In our last example for this section, we're going to look at an arithmetic example. Namely, we're going to look at z mod 8 mod the ideal generated by 2. So the question is, what is this? Now, the ideal generated by 2 is, of course, just all multiples of 2 in z mod 8. And if you look at all multiples of 2, you'll find it's 0, 2, 4, and 6. I'm not going to write the bars. So what is this? Well, we're going to do something slightly different. We're just going to figure out what it is first, and then we're going to apply the Noether isomorphism theorem to see what it is again. So let's look at cosets here. So 0 plus 2 should be the same as 2 plus 2 should be the same as, should be the same as 4 plus 2, which should be the same as 6 plus 2, because all of 0, 2, and 4, and 6 are in the ring, or sorry, in the ideal. And then we have 1 plus 2, but 1 plus 2 should be the same as 3 plus 2 because 3 minus 1, that difference is 2, which is in the ideal. And similarly, that should be the same as 5 plus 2, which should be the same as 7 plus 2. And all of these, this is just 0, 2, 4, 6, of course. And these guys, if you sit there and you write them out, you'll find they're all 1, 3, 5, 7. So it seems to indicate that, well, we've exhausted all the cosets, right? Because we only go up to from 0 to 7 as our representatives. It seems to indicate there's only two elements, that there's 0 and there's 1. And in particular, this should tell us then that z mod 8 mod 2 is the same as the guy that only has 0 and 1, where the arithmetic is kind of like normal. So we should get F2 out of it. And if we sat here and we computed the addition table for 0 plus 2, 1 plus 2 is our columns, 0 plus 2, 1 plus 2 is our rows, and we computed the multiplication table, 0 plus 2, 1 plus 2, 0 plus 2, 1 plus 2, what we'd find is the usual. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 2, but 2 is in the ideal generated by 2, so we get 0 plus 2 out of that. And then here we'd get zeros everywhere. And then we get 1 in the last spot. 1 times 1 is 1. And this is for this guy here. If we want to do F2, then what would we get? Well, we'd do 0 and 1, 0 and 1. And we would do, again, 0 and 1, 0 and 1. And we would get 0, 1, 1, 0. And we get 0, 0, 0, 1. What's different about these addition and multiplication tables? And the answer is nothing, really. It's just how we represent the elements. The actual arithmetic is the same, as you can see. We just represent the elements differently. And so this would tell us then that they're isomorphic, and you can define an explicit isomorphism. It's going to take 0 plus root 2 to 0 bar, and it's going to take 1 plus root 2. I'll put the bars in the F2 just to emphasize they're sort of different elements. We'll take that to 1 bar, and that map will be an isomorphism. Why? Well, look at the arithmetic. It's the same. So that's one way of going about it. Alternatively, we can try to, let's see what I call that function, phi. We can try to define a homomorphism from z mod 8 to F2. And I'm trying to emphasize that something interesting happens and we get a field in this case. And what that's going to do is it's going to be, I'm going to take my A and I'm going to reduce mod 2. So this is sort of further reduce mod 2. That's our function. Now, z mod 8 itself is equivalence classes. This is like z mod the ideal generated by 8. So things here look like A plus 8, right? Now we don't think like that necessarily with Z mod n, but that's ring theoretically what elements there look like. So we have to check that this function is well defined before we prove it is an epimorphism or anything like that. So let's do exactly that. So let's suppose that A is congruent to B mod 8, then B minus A is some 8k. So f of so B is A plus 8k. Let's write that out. B is A plus 8k. So f of B is f of A plus 8k. But reducing mod 2 is a homomorphism from Z to Z mod 2. In particular, this 8 guy, this 8 that shows up here, is going to reduce mod 2 to 0. So we're going to get f of A out of it. So if two guys were congruent mod 8, that is, they represented the same coset or the same equivalence class, f will further reduce them mod 2 to the same thing. Okay, so f is well defined. Moral homework, check that f is a epimorphism. It's not hard. You do a similar argument to this. That it's onto just comes from the fact that 0 goes to 0 and 1 goes to 1 in this ring under f, and the only elements on the right are 0 and 1, so you hit everything. Okay, great. Now let's look at the kernel. So let's suppose that, well, certainly, let me say this first. So certainly the ideal generated by 2 is in the kernel of f. Because if you have a multiple of 2, f is a homomorphism, so that's f of 2 times f of A, and f of 2 is 0 in f2. So we get 0. All right, so that's showing that it's in the kernel, and there's lots of ways of showing that they're equal. I'm going to do something silly. So the only other elements that we miss that the kernel of f could contain are sort of the odd looking elements. So if sort of 2a plus 1 was in the kernel of f, so if you happen to have like an odd element, something that was missed by the multiples of 2, then f of 2a plus 1 is f of 2a plus f of 1 is, well, f of 2a is 0 by that previous part, plus f of 1 is 1, so you get 1 as an output, but it's in the kernel, so 1 should be equal to 0, and that's a contradiction. Let's use our blue lightning. Okay, so this is saying that the kernel of f contains only even elements. It cannot contain an odd element. So in particular, the kernel of f is exactly the ideal generated by 2. All right, so the Noether isomorphism theorem then tells us that we have an isomorphism from Z mod 8 mod 2 to F2, and that isomorphism is very explicit. It's explicitly given. It's given by take your coset representative and send that to the further reduction mod 2 of that coset representative.